It's still hot down here. It got up to 93 today, so
Ooh,
Really?
we had the
Wow.
we had the coldest August on record here. So
we had one of the hottest record August on record. Yeah.
and we had one of the driest August on records.
Oh, we're there too, buddy. We're there too.
Yeah,
Yeah.
we need rain
Yeah.
and
Where are
water
you,
Well,
Don? Is that Virginia?
near Philly, near
Okay.
Philadelphia.
New Philadelphia. It's that drive.
Water,
Wow.
I'm watering my garden every couple days.
So you're like me, you're praying for a hurricane.
Yeah, that would help.
That's what
That would be
I'm
good.
praying for
Yeah.
now. That's the only thing that can break our drought is a
I
hurricane.
don't think that's what he
well,
said. No.
no, no. Watch what you wish for.
Hey,
Yeah.
it's usually below Cat 1 when it hits us, so we're safe.
Yeah,
I,
that's
it's the people when it hits Houston and New Orleans, they've got to worry
yeah,
about it.
yeah, that's for sure.
I'm just hoping it holds together long enough to get to us usually. Uh,
Okay.
yeah, you like your black hole theme. That's pretty cool.
Isn't that
Yes.
cool?
Yeah.
Yeah.
Considering that's what I'm talking about tonight, that's exciting.
Yeah, that's your theme.
Yeah.
That's your theme tonight.
Yep.
Hmm.
That's a theme. Yeah.
You know, I always get sucked into any kind of black hole lecture. I mean, really.
Is there a pun intended there?
I'm pretty sure there
Apparently,
is.
it didn't work very good.
Yeah,
Yeah.
there's a fun.
There's some
Yeah.
new research out on
Not working
If
good.
he'll be have his eyes closed when I'm giving my presentation. We'll know it was a fun.
Right. Holding on for dear life. Yeah.
Yes.
Is my
I
audio
gave.
okay?
Yep. You're
Yeah.
good.
Thank you.
I gave a talk Saturday night, and they had a lot of questions about black holes. You should have been there, Scott.
Hmm.
Should have been there.
Should have been
I could have
there.
given him a whole bunch of puns.
You think, yes, you are good for this.
Yes, I am. That's cool. All right, so I'm doing a little bit of sharing right now. We are live, and let's go ahead and bring myself on. Hey guys, here we are.
Hi.
This is Scott and Terry. Scott Roberts from Explore Scientific, Terry Mann from the Astronomical League.
Last names.
That's right. You have a really cool shirt on, Terry. This looks like
Badlands. Yeah, dark sky.
very cool.
Yes.
Very
Thank
cool.
you. Yes, I'm getting blinded by the sun here. I'm outside.
It doesn't.
I
Oh,
should,
it looks like you're in the studio, like in a library or something. It's kind of surreal. You got the Milky Way behind you, city
backlighting.
night lights. Yeah.
Yeah.
I thought
Yeah,
that
but
was like
nice.
you see her background, I thought that was like the supernova
Yeah.
going off in the next, in our galaxy, brightening her side.
That's right. Right. So would we get supernova burned if a supernova is really close by? I guess we would.
Sure.
Right?
It's close enough.
Close enough. Is there anything close enough that might go supernova?
Not
Chicago?
really. Not really.
Oh, thank God. Okay. All right. So,
I think-
anyways, this is the 52nd Astronomical League
Yes.
Live, right?
Yep.
Okay. Well, Terry, thank you for letting me host this program or be the man behind the curtain. You're actually the host, and I'm going to turn it over to you.
Well, thank you, Scott, but you're not exactly the man behind the curtain. You're
No
in front of the
attention to
curtain,
him.
front and center there. Well, hello, everybody. Thank you for being here. As you can tell, we're all in prime form tonight. We do have two Scotts on here, so it's going to get a little confusing. We have Scott Roberts and Scott Harrington, which we're glad to have both of them. We also have Don Knabb and Chuck Allen, president of the Astronomical League. So what I would like to do is go ahead and start. David Levy might be here a little bit later, and he might not be able to show up at all. We will miss him if he doesn't, but people do have other things that they need to do sometimes. So let's start off with Don Knabb. Don, thank you for coming. Appreciate you being here. Really look forward to your talk.
Well, thanks, Terry. I'm going to change things up a little bit tonight. Not going to do the night sky highlights. Instead, I'm going to talk a little bit about Astrocon. For those who weren't there, talk a little bit about Astrocon. So let me share the screen. Slideshow. In the beginning. Coming through okay?
Yes.
Okay, so just a few slides about the event back in June. Is that right? Goes back that far?
Yeah.
Time flies. So a quick report on Astrocon in case for those who haven't been there. So the league holds what we normally call Alcon, but this year we called it Astrocon. And this year was at Ruby's Inn, just outside the entrance to Bryce Canyon National Park in Utah. It was my first time there, and it was an amazing, amazing trip. So, and it was planned to be at the same time as the Bryce Canyon National Park Astronomy Festival. So Ruby's Inn is a historic inn. It's only about 2 miles from the entrance to the park. Here's a little view of the inside. You can see this is the lobby where we would check in, and it's a great facility. It's big. It's got multiple outdoor buildings, you know, separate from the main hotel. And we had a good breakfast every day, and it's a full service restaurant for lunch, dinner, and breakfast. And also, there's a lot of campers in. Well, Ruby's Inn has an RV and camp park, and of course, in Bryce Canyon there are a lot of campsites. So they have a huge grocery store. It sells pretty much everything you want as a camper or a tourist. And it's an amazing place. I'm so glad that Bryce Canyon was picked for the location. Never been there. It was a great chance to get there. My wife and I traveled out with the president and his wife of our astronomy club. So we went into the park most days. I'll have to admit, we did play hooky one day and went down to Zion. Couldn't resist that chance. But we were in the park every other day. And if I had to pick one word, I would say it was otherworldly. It was like being on Mars. So here's a view. One of the vistas is around sunset. The first night, I think we were the first full day we were there. We didn't get to the hotel about midnight, so it was late night when we traveled. But it's some amazing things to see every day. For a geologist, this would be a trip to heaven. It really would be. It's just one amazing vista after another. Here, there's a huge walkway that takes you out to the big vista. I guess this is called Bryce Point. And you can just stand there for an hour and just look at the terrain. If you look in the upper left part of my slide here, that's not a cloud. That is actually smoke. But you see smoke across all the top. We had some pretty bad smoke most days, not every day, but most days, because of forest fires all across Utah, and one just 10 miles south of the park. But it is just I could stare at this vista all day long, and you can actually hike all the way down into this valley. We didn't do that, but there's plenty of hiking trails. So each day at Astrocon, we'd have presentations through the day, sometimes concurrent, more than one at once, and every night you could do night sky observing at the park on your own, or the last couple of days of the week, the Bryce Canyon Astronomy Festival was held at a parking lot across from the visitor center. So here's a shot of that parking lot, and this is where we're just getting set up. We didn't go down there every night, but we went down there one night because the president of our club carried his Quest Star with him out to Utah, and we probably had, I'm gonna guess, 24 scopes at least set up here. So this is a shot of my friend Dave Hockenberry's Quest Star at the park, and he spent I'm trying to guess from when it got dark to almost 11, just showing the double in Lyra, and I think he was getting pretty tired of it because we had like 800 some people come through that night. It weren't good until about 11 o'clock or so, and 10:30 or so, smoke started to roll in. Here's a shot of the moon that my wife took as it was setting at the star party. So yeah, the night skies were definitely affected by the forest fires. I took this shot on the way back up from Zion. I think we went there on Thursday. Yeah, this fire is only 10 miles south of the hotel, and but the night we had the public star party we went to, it was good, and the smoke came in 10:30 or 11. So we had good viewing for 850 people attended, and this was a multi-day event, so this was just one night. After the banquet, the Saturday night banquet, we had to get a little more stars in our eyes, so we went down to the far end, I think they call it Rainbow Point, the far end of the park, about a half-hour drive or so, and that's at 9,000 feet. So I have to say that was the most clear sky I've ever seen in my life, and it was amazing. The Milky Way was just a river of light across the entire sky. So it was worth the trip out to just for that view. It was amazing. Oop, let me go back one. That's a picture of how the sun looked like most days when we had the smoke coming in. And you could actually smell the smoke most days. So during the convention, every day we had a bunch of different presentations, and I attended many of them. We had our Astronomical League business meeting. I was there for that. Here's a shot of Dr. Shane Larson giving a presentation. He has been I saw him speak also at Green Bank StarQuest. Very good presenter, very, very engaging with his audience. Great presentation. And there was solar observing every day for a couple hours at Ruby's Inn, just outside the entrance to the grocery store. This is my friend Dave Hockenberry, the president of our local astronomy club that I belong to here near Philadelphia. So it was an amazing trip. This is my last slide. Just want to show you, I don't know if you can see them, but there are smiles on all of our faces. That's my wife Barb, and there's me tucked in here, and my friend Dave and his wife Ann. And I don't know if you can see the smiles, but we had a great trip. And the organizers deserve a lot of credit. They did a wonderful job setting everything up. All the presentations I saw were great. So next year we're going to Cincinnati, and the year after that, Colorado Springs. So I would say if you can fit in your schedule, definitely attend. The Astronomical Convention is a great event, and I plan to keep going to them. So that's all I had, Terry.
Okay, well, thanks, Don, and I agree with everything you said, and Cincinnati will be amazing too. Chuck, at this point, I think I am going to go to you and let you go ahead because you can kind of piggyback right on what Don is saying.
Fantastic. Thank you, Terry. Good evening, everyone. Let me share a screen here. Okay. You see that, everyone?
Yes.
Okay. There are three conventions I wanted to talk about a little bit. One's coming up next weekend near Mansfield, Ohio. It's the Hidden Hollow Star Party and Great Lakes Region meeting. They have, of course, hosted this event every September for as long as I can remember. I first met David Levy at one of these events up hosted by the Richland Astronomical Society. Registration's open, costs $60, and well worth it. There are talks during the day and observing at night, and some of that observing, if it's clear, involves the use of Big Blue, which is their 36-inch reflector at the Warren Rupp Observatory. It's a very, very nice convention. So if you're free next weekend and you're near Ohio, come see us. The North Central region of the Astronomical League always holds fantastic regional conventions. I went to theirs in Minnesota this past year, and went to their convention the year before as well. And they're really well-run events, and they've been going on for decades. And next year it will be hosted by the Cedar Amateur Astronomers in Cedar Rapids, Iowa. And the dates are May 15th through 17th. It will be hosted at the Doubletree by Hilton in Cedar Rapids on those dates, with lots of access to the Eastern Iowa Observatory that they use. And I gave a talk in their meeting room in the background there on the left. And it's really an incredible facility. They have spectroscopes there and demonstrations of all kinds for young people, and set up lots of telescopes on the outside as well. Beautiful, beautiful facility. And I hope if you're free next May, you'll join us there. And as Don alluded, we'll be meeting for our national convention in Cincinnati and Covington, Kentucky next year, on August 12th through 15th. The hotel is actually across the river from Cincinnati in Kentucky and has this view of downtown Cincinnati. There's a walking bridge and driving bridge that leads right into downtown, and we have free trolleys that will take you into Cincinnati to the Banks District, to a Reds game, or over to Newport for the aquarium. These are some of the attractions that are very close to the hotel. The Reds will be in town. If you've never seen a pro baseball game, you might want to opt for that. There'll be lots of other options, however. And this is the Banks District, right across that bridge. And again, there are free trolleys that take you there. And the ballpark is right next to this. So lots of entertainment in this area, lots of nice restaurants. And the Newport Aquarium is something really spectacular to see, and also on the trolley line that will get you there. Further out, if you're into museums, there are all kinds of museums in Cincinnati. Children's Museum is fantastic. The zoo is fantastic. And I would highly recommend the American Sign Museum if you have interest in sign history. They have many observing facilities, one of which I cannot show you, but it's something that will be advertised a little bit later as the convention plan comes together. But it involves a very sophisticated observatory, and I'll just wait and let the Cincinnati folks tell me when they want to release that information. Coming to our conventions is an opportunity to support young people as well, because we have lots of awards that we give to young people for research. These were two of our NIA winners in 2023. And we, of course, NIA, the National Young Astronomer Award for Research, is sponsored by Scott Roberts and Explore Scientific, for which we are eternally grateful. And he supports our Wilhelmina Fleming awards also for imaging. And it's also an opportunity just to meet old friends. And one of the great friends that I've made in the last couple of years is right in the foreground here in the blue shirt, and that's our speaker tonight, Scott Harrington. I first met Scott or introduced myself to him via email back in 2019. And that's because I was researching naked eye visibility, visibility with binoculars, visibility with telescopes of certain sizes, to find out what the faintest objects or furthest objects were that could be viewed.
Oh, you're just hearing this thing all the time.
Levels of equipment. And I found this site, 250 plus deep sky objects visible with 7 by 35 binoculars in the naked eye, the result of years of research that Scott had done from his family farm in northern Arkansas with very, very excellent skies. And he's a consummate observer, as you will soon see. But this is a typical page that he put together, marking the difficulty with observing particular classes of objects, in this case, galaxies, either with the naked eye or with binoculars. And I thought it would be a great idea to invite him up to my club, the Evansville Astronomical Society, to give a talk in 2019. And he and his brother Kyle came up, and then we went on a trip after that. They were interested in museums, and I said, well, I've taken lots of people to DC over the years since my days in the Air Force in Delaware. And so Scott and Kyle and I took off for DC for 5 days and saw everything, including pandas, while they were still there. And it was a great trip, and learned during this period of time just how seasoned an observer Scott had become. So he became a regular speaker at multiple conventions starting in 2022. He and his siblings in various combinations have gone with me to our last 4 conventions, and Scott has spoken at all 4. And here he is with Harrison Schmitt from Apollo 17 at our Albuquerque convention in 2022. And so what I'd like to say is that Scott has begun to distinguish himself, or already has distinguished himself, as one of the principal observers, but also writers in our community. And to emphasize that point, I'll show you just a few of the, I think, 8 or 9 articles that he has written for Sky and Telescope magazine. Here's one, Araga Has It All. It's in the magazine. Here's one, Springtime Neglected Binocular Galaxies, in another issue that came up. He wrote one about IC10 in a Sky and Telescope magazine. But more importantly than that, he's had 3 cover articles. He had a cover in 2021 called Stellar Nurseries. That's his article appearing on the cover. He had a cover article, I think, 2 years later on the Triangulum Galaxy M33. And most recently in May, a cover article on starburst galaxies. And in this particular article, Diana Hanna-Kanen, who is the new editor-in-chief, had this to say: "It was but 4 years ago that I shepherded the debut article of a certain young observer through our publication process. That article was vibrant and refreshing, reflecting the enthusiasm of its author. The writer, Scott Harrington, has consistently submitted articles of high caliber during those intervening years. And this month, as we did 4 years ago, we're featuring his article on the cover." Diana recognizes him because he is now the youngest contributing editor at Sky and Telescope magazine. He's also written for Amateur Astronomy magazine and for Reflector, and he's just an amazing young astronomer. So I'll turn it over to Scott for his talk tonight on the nearest black hole.
Thank you, Chuck. I appreciate that. Yeah, that's not gonna lie, that wasn't biased at all. You know, he's very sweet to say all that about me. But I really appreciated what he did there. I've definitely grown a lot, and thanks to him, I've gotten a lot there. Trying to see if I can get this. Just give me a second to share my screen here. Boogers. Okay, there we go. So, is that appearing well on your side?
Yes.
Okay. So before I begin, I just want to say that it's an honor to get to be on the Astronomical League Live. I enjoy watching them. I sometimes don't always have the time to catch them live, but they are recorded. The one from last month I've found very inspirational. I had to reach out and send Bob King a personal email after that, because his presentation was so timely, being on Saturn. And thanks to him, I was inspired to take my my Canon image stabilized 15 by 50 binoculars, and I was able to hunt down Iaptis, the Saturn's moon that goes from one side of it to another, and it changes its appearance because it's tidally locked. So one side is dark, one side is bright, and when it's on its bright side and at greatest elongation, it's magnitude 10.2. I was able to see it in the binoculars. So I've seen two moons of Saturn in binoculars, and so I encourage anybody to watch these League Lives. I always enjoy what I can learn from them. So this is my presentation. Where is the nearest black hole? I'll be honest, I'm not an astrophysicist. I don't have a degree in it or anything. I just, whatever I get, I pick it up. And I don't even find black holes as fascinating as others. This is mainly because I'm a visual observer than an astrophysicist. So for me, it's all about going outside, and then later I do the research and get more into the science part of things. But last summer, I read an article about a black hole that was recently discovered less than 5,000 light years away. And when I read things like that, I start to wonder, well, where is it in the sky, or what star does it orbit? And I start to kind of question. So I dig into it. And so it got me thinking about it more, and I started a little research, and I wanted to know what other close black holes, And I found it so enjoyable to keep working backwards from what we know now that I found myself in the 1940s. in the history back that far. And I could have gone further, but at this point, I decided to stop going backwards and start piecing together a coherent narrative. I was so excited by what I learned. And so that's what this talk is about. It's about what I learned, and basically all of it was new information to me. And so I'm assuming some of this is going to be new information to others too. So I hope you enjoy it. Um, so where is the nearest black hole? That's a question. It's an ominous question that astrophysicists and science fiction writers alike have spent the last half century or more pondering, since you really, really, really don't want to be near one. But even though we've imaged the silhouette of the one at the heart of M87 and our galaxy, like you can see in the first slide there, in the 1960s, in the lifetime of my father, in the 1960s, the mere idea of a black hole or even a neutron star was still just a theoretical curiosity. I didn't realize it. I thought they'd had some of this nailed down before, but no, it was only theoretical. And so only after astronomers decisively proved in 1969 that a very blue 16.6 magnitude star at the heart of the Crab Nebula was a neutron star. Only then did the reality of black holes take hold. Detecting them would be far harder, though, since Stephen Hawking predicted in 1974, a few years later, that the only electromagnetic radiation they emit is a tiny sliver of thermal radiation, now known as Hawking radiation. Thus, astrophysicists searching for them would have to rely on indirect observations, because unlike the neutron star, it's not producing any light of its own that you can hardly see. So, and so we didn't know, theoretical. Now we can detect some of their, the disk around them. But so I mentioned electromagnetic radiation. Um, in that, in the electromagnetic spectrum, the three types of radiation with the shortest wavelengths, thus at the high frequency end, frequency is how often it they repeat from high to low, and so the ones that can basically do the most penetrating are ultraviolet, X-ray, and gamma ray. They have the highest photon energies and are called ionizing radiation because they're able to ionize atoms, causing damage to living tissue via chemical reactions. However, except for the very lowest energy range of ultraviolet, known as UVA along with some UVB, all three forms of radiation are absorbed in the Earth's atmosphere. To be specific, it's the oxygen and nitrogen atoms in the thermosphere, where the International Space Station orbits, that absorbs nearly all X-ray and gamma rays, with the mesosphere and stratosphere screening the remainder. So to detect where in the universe besides our sun such radiation may be found, astronomers knew they'd have to get instrumentation above the von Karman line, which is 100 kilometers, basically space, so they wouldn't be blocked. But while Germany had already succeeded in sending a V-2 rocket beyond this point in 1944, it would be longer before rocket-borne detectors were ready. One of the men working on this issue in the 1950s was an Italian-American named Riccardo Giacconi, who would go on to receive a share of the Nobel Prize in Physics for, and I quote, pioneering contributions to astrophysics, which have led to the discovery of cosmic X-ray sources. So, on June 18th, 1962, Giacconi, along with Herbert Gursky, Frank Paolini, and Bruno Rossi, watched as the U.S. Army launched an Aerobee 150 sounding rocket, carrying their payload consisting of 3 large area Geiger counters. Basically strapping Geiger counters onto a rocket. It took place at 11:59 p.m. local time from White Sands Missile Range, New Mexico, with the intent of studying, and I quote, fluorescence X-rays produced on the lunar surface by X-rays from the sun, and to explore the night sky for other possible sources. That was interesting. When I read that, I was like, wow, they thought they didn't know what they were doing to some degree. They were just being scientists and just taking risks. and they thought maybe the sun would be producing X-rays and the moon didn't have an atmosphere, and maybe they'd cause some rocks on there to fluoresce. You understand, this is 1962. This is before we landed on the moon. This is when we still weren't truly sure if, we put something on the moon, it wouldn't just sink in. This was still a pretty broad time where we didn't know much about it. So they were taking a shot, and with the moon one day past full in Sagittarius, because they were after the moon to some degree, they were surprised to instead detect a strong signal southwest of the moon in the general direction of the galactic center. However, since their instrumentation was not equipped with collimation to restrict the field of view narrowly, the signal was too broad to produce a precise position. So they didn't know exactly. Okay, but so they're scientists. And so Giacconi and his team decided to repeat the experiment again in October, when the galactic center was below the horizon. This time, the strong source was not present. A third attempt, then the following summer, in June of 1963, verified the results of the first flight, confirming that a discrete source of X-rays existed in the general direction of the Milky Way center. Okay, so you're probably thinking, yeah, I think I see where this is going. But this is the interesting thing. In 63 and in 1964, a different team, one led by Stuart Boyer, made several launches with Geiger counters aboard Aerobee rockets. So he somewhat repeated the experiment. But their detectors that he used were about 10 times as sensitive and collimated. So they were able to pinpoint the strong source that Giacconi and his team had found is actually lying north of Antares in Scorpius. As you can see in the right-hand image there on the slide, they were able to get better when it rolled and picked up signals. They were able to mark them and figure out where they are, and they were more precise because they picked up Sagittarius A, Cygnus X, Cygnus A. They different ones, and so they knew more of where this was happening. And their source that they marked is marked as I, which is to the upper right of what's marked as Sagittarius A. So they went ahead and dubbed it Scorpius X1, the first extrasolar X-ray source discovered. In 1966, the area around Scorpius X1 was searched for with telescopes on the working hypothesis that its source, you're looking for what's producing all these X-rays, its source would look like a star of 13th magnitude or brighter and emit an excessive amount of ultraviolet light. Lo and behold, a 12.6 magnitude star with a small variability, thus that variability is why it's in the AAVSO archives as V818 Scorpius. And this is I looked at this star because of Bob King. He wrote about it. So I thank him for teaching me some of this. And when they found it, it shone brightly in the ultraviolet, and that's what they were expecting, and found within 1 arc minute of the X-ray source. The very next year, Soviet astronomer Joseph Shklovsky published a paper in which he accurately modeled what was producing the X-rays. He believed the best explanation, based upon all the observations made, was a binary system composed of a neutron star orbited by a secondary component. After the material is pulled off the donor star by the neutron star's intense gravity, it forms an accretion disk around the neutron star before falling onto its surface. But as the matter accelerates and impacts the neutron star, the resulting friction generates vast amounts of electromagnetic radiation, mainly X-rays. On a side note here, it should be noted that it was disputed for a long time as to who should get primary credit for the idea that Scorpius X1 was a binary system, with a neutron star accreting from a companion. While Shklovsky, who died in 1985, is frequently credited, the idea did appear in a paper by another Russian around the same time. Either way, it's safe to say that the Russians figured it out, congratulations, and that the idea that neutron stars and black holes can produce prodigious amounts of X-rays via an accretion disk, when in a binary system, simply did not exist before the discovery of Scorpius X1. Only after analyzing its observed properties was it formulated. I didn't know that. I thought, theory came first, observation second. Here they actually observed it and then came up with the theory afterwards that matched. Thus, one can also say that without a doubt that the advancements in rockets made during World War II would go on to do the same for our understanding of black holes decades later. Strange coincidence. So this the second brightest X-ray source, because like I showed you, they discovered more than one. Well, the second brightest was discovered by Stuart Boyer and his team, appeared to come from an isolated discrete object, coincidentally only several degrees from Cygnus A, one of the strongest radio sources in the sky. That source, known as Cygnus X1, was searched for in vain on images taken with the largest telescope of the day. Astronomers were puzzled that no star of peculiar ultraviolet intensity could be found in the area, since it had recently worked in the case of Scorpius X1. Soon, though, Cygnus X1 would become one of the most studied objects by astrophysicists and theoretical physicists alike. You see, the early 1970s was an exciting time for those intent on studying the so-called X-ray universe. And it started off at a fever pitch with the launch of Uhura, NASA's first X-ray satellite, in December 1970. This was all thanks, in large part, to Giacconi, who not only conceived of the orbiting observatory, but directed its development. Within a few months of its launch, the Uhura team had discovered erratic sub-second variability in the X-rays emitted by Cygnus X1. This immediately led them to believe that it was a collapsed object, such as a neutron star or black hole, since these were the only objects believed to be able to create such pulsations. In 1973, a team obtained enough high dispersion spectra of the ninth magnitude star that they disagreed with the idea that the emission line singly ionized helium arose from the unseen secondary companion. Instead, they believed that, like Scorpius X1, the emission originated in a gas stream falling towards the secondary, creating the accretion disk which was producing the X-rays. But you have to remember, all we see is one star, but they're thinking that something is being pulled away from that star. So before long, all the evidence indicated that Cygnus X1 was most likely a black hole. But here's interesting to remember. While theoretical physicists Stephen Hawking and Kip Thorne were 80% sure that Cygnus X1 was a black hole in 1974, it wouldn't be until 1990 before both were 100% certain. So before I was even born, we were confident 100% that this was a black hole. Recent observations by Miller Jones of the International Centre for Radio Astronomy Research at Curtin University, Australia, Miller Jones and colleagues, they were able to show the black hole resides over 7,000 light years away and has the mass of 21.2 suns, making it the second largest stellar mass black hole ever found without the use of gravitational waves. See, gravitational waves, they can detect really big ones because it takes big ones to be able to, vibrate gravity that way. But this one, it's pretty large. It's still what they call stellar mass, which is like below the 40 or 50, suns mass. But it's quite large, and usually you would take gravity waves to start detecting that. So it orbits a 40.6 solar mass primary. So the primary is actually larger than it by about twice in mass. It orbits it every 5.6 days, all the while being a strong, persistent source of X-rays due to the primary source of accretion coming from the stellar wind of the O-type supergiant. So basically, it's got a fuel tank next to it that's just infinite. So it can keep siphoning off at a heavy rate, persistent. It's not got some wimpy star where it has trouble, giving it what it needs. it's going to go for a long time. And here's interesting. It's likely the black hole formed from a star that started between 55 and 75 times the sun's mass. So it was larger. It was actually the primary originally in the binary system. But it lost more than half of that via stellar winds by the end of its fusion-powered life. So like these stars are always just like losing material all the time. That's kind of how we get auroras. That's how we get because they're always pushing off material. So even then, after losing that much, more than half of its mass, it was still massive enough to collapse it into a black hole without going supernova. Usually they have to shed the final amount of mass and collapse inward. This thing was so massive, even after the end of its life, it just went straight down. It just collapsed. And it's estimated that the star lost only about a solar mass during the collapse. It's blink of an eye, it didn't hardly lose anything. It kept most of it. The black hole's fast spin, the system's alignment, and its steady pace through space also supports Cygnus X1's supernova-less end. So it's very strange. You'd expect to see a supernova remnant here, but we don't find one. And so that's where they've had to work in the theory that this is a different one. All right. So remember I talked about, how Scorpius X1 is slightly variable, Cygnus X1 doesn't seem to really be variable. It is just barely, that's why it's got an AAVSO designation, but Cygnus X1 didn't hold the record of closest known black hole for as long as you might think. That's because on August 3rd, 1975, now we're into the mid-70s, the Ariel V satellite detected an X-ray source in Monoceros that rapidly increased in intensity, soon becoming brighter than Scorpius X1, which, as I just got done saying, it's the brightest X-ray object in the sky from our perspective. So this became brighter than that. That was exciting times. And with an accurate position in hand, astronomers quickly looked for it using optical telescopes and were amazed to find a star that appeared at magnitude 12 or brighter, even though on Palomar Sky Atlas prints it was barely visible. Thus, the X-ray source A0620-00 had an optical counterpart known as Nova Monoceros 1975. The nova, which peaked around magnitude 10.5 in late August, man, I would love to see that in my binoculars, was searched for on photographic plates archived at Harvard College Observatory. A trio led by Lola Achius looked at over 5,000 plates taken from 1898 until 1975 and discovered that in late 1917, a star appeared at the same position and reached very nearly the same maximum brightness. This garnered it the rare title of recurrent nova, like TCRB, but it would eventually lose it as its true identity was revealed. It's not like TCRB. And 15 months later, after it had reached its peak brightness, the optical counterpart had almost fully returned to its pre-outburst brightness of 19th magnitude. In their 1986 paper, Jeffrey McClintock and Ronald Remillard came to the conclusion that A0620-00 was a low-mass X-ray binary comprised of a K-type dwarf orbiting a black hole with a solar mass between 3.2 and 7.3. It was found also that the orbital period was just 7.75 hours. So that the K-type dwarf it's orbiting a black hole and it's whipping around it in less than 8 hours. And it's a black hole with, more mass than our sun, just shrunk down. However, unlike Cygnus X1, they believed it was, and I quote, unlikely that the accreted gas is flowing continually onto the compact source because no X-rays are detected in its quiet phase. So that's where there's a difference where it's just a little K-type dwarf that's smaller than our sun, and so it doesn't really have what it takes to keep pulling off of it at such a rate they can go very often, and they just don't even detect X-rays from it when it's down in 19th magnitude. So today we understand that A0620-00 lies some 4,700 light years away, and it held that record for the closest known black hole until 2022, when it was dethroned by one over 3,000 light years closer. So I didn't realize that. I didn't know. I just thought it was so cool that this little known black hole that we just, you understand, we wouldn't have known that it was there if it hadn't, brightened at that point. And so it's strange that, it held the record for so long out of kind of a fluke that we caught it during an outburst. Okay, so I mentioned distance, okay? Now I need to tell you about acquiring accurate distances. The best of the best are achieved through parallax. But before Gaia was launched, that's the European Space Agency's satellite I'll talk about here in a second. Before Gaia was launched and set an extremely high bar, astronomers had to be content with very long baseline interferometry performed by radio telescopes. In 2009, about the time I was getting interested in astronomy, professional astronomers used 3 radio telescopes to create what at the time was the most accurate model independent. That's an interesting word, model independent, because that just means they didn't run it through a computer and have the computer models and then pick out which one's the most average. This was independent of any models. It did distance estimate to a stellar mass black hole. This was the most accurate at the time, 2009. Using the Green Bank telescope in West Virginia, the Very Large Array, known as the VLA, in New Mexico, and the Effelsberg telescope in Germany, they found that a star system in Cygnus, harboring a 9 solar mass black hole, was 7,795 light years away, a little further than Cygnus X1, and they knew that distance, give or take, a mere 457 light years. So just say about 500 light years, give or take. That's how good they were at the time. This was impressive, okay? Known as V404 Cygni, it first caught the attention of astronomers in 1938 as a nova that reached 11th magnitude before erupting again in 1956, 1989, and 2015. And it continues to fascinate since, as of a year ago, astronomers discovered it's a rare triple star system, meaning one black hole, 2 other stars orbiting. So that's a fascinating one. And as you can see in that image, that because the way it works, it's just created those novas. When they go off, they create these little shells, and they can see them in using certain satellites. All right, so now we're going to talk about Gaia briefly. On December 19th, 2013, well over, a decade ago now, but almost 34 years after the launch of the Hubble Space Telescope and 8 years before the James Webb Space Telescope, one of the most sophisticated telescopes ever made was launched. Built by the European Space Agency, the observatory is named Gaia and consists of 2 rectangular primary mirrors, 1.45 by 0.5 meters across. It was designed to collect astrometry, that word, I'm going to skip that word, astrometry and photometry with unprecedented precision, and it did. However, its mission is now complete, and back earlier this spring on March 27th, the European Space Agency powered down the spacecraft and sent it into a retirement orbit around the sun. So, the spacecraft's operations are now over, but the scientific explorations of Gaia's data has just begun. One area is finding so-called quote-unquote quiet black holes. You see, for every black hole that boldly broadcasts its presence via X-rays, countless others keep things on the down low. In fact, the entire Milky Way galaxy only has an estimated 1,000 black holes like Cygnus X1, making noise, allowing us to see them in X-rays, versus roughly 100 million X-ray quiet black holes. So basically, if there's no companion, how are you going to get a signal from it, So on June 13th, 2022, Gaia scientists put out the spacecraft's 3rd data release. And Kareem El-Badri of the Harvard-Smithsonian Center for Astrophysics and his colleagues already had telescopes lined up in both the northern and southern hemispheres to track any luminous star that seemed to be orbiting an invisible object. This was possible by exploiting the facts that A, massive companions have larger orbits at fixed period due to Kepler's third law, and B, dark companions produce larger photocenter wobbles than would luminous companions of the same mass. So if they're looking for a wobble here in the data where it showed that the star had moved, but it never registered a companion around it in invisible light. But Gaia observes more than 1 billion stars. So Al-Badri said even if the data are very good, you expect things to go wrong in some cases. And so when you're looking for something rare, you usually assume that most will be dominated by false positives. And, in fact, one by one, most of the few suspicious objects in the Gaia data proved to be nothing special. At first, that also seemed to be true for a yellow sun in the constellation Ophiuchus, bearing the unmemorable name Gaia DR3 437346535241530162. The star shines between the local arm and the Sagittarius arm. So, it's in our vicinity. The Sagittarius arm is the next spiral arm towards the galactic center from our own. The Gaia data suggested the star was going around something dark every half a year. And El-Badri, he explained simply, initially we thought there was a very good chance it's wrong because a period that's an exact fraction of an Earth year could arise from some elementary error. It just seems too like, oh boy, something's probably wrong. As it happened, the Large Sky Area Multi-Object Fiber Spectroscopic Telescope, LAMOST, in China, had recorded the yellow star's radial velocity twice, in 2017 and again in 2019. Both times the velocity was similar and resembled what Gaia itself had measured for the star. It looked like it hadn't moved very much, Al-Badri said, so we thought, it's probably a dud. After all, if the star was really bound to a black hole, then the star would have to be moving quickly to keep from falling in, so its radial velocity should always be changing as the star zooms one way and then the other way around in its orbit. The Magellan Clay Telescope in Chile then observed the star on July 6, 2022, finding a much higher velocity. So then we really started to think, okay, maybe it's real, Al-Badri thought. But trouble lay ahead. See, I'm from the Northern Hemisphere, so I don't think of this much, but July in Chile is winter, and a blizzard closed down the observatory. The next measurement, made elsewhere more than 3 weeks later, indicated that the star was racing around something no one could see. With every additional velocity measurement we got, El-Badri said, we became more convinced that it had to be a black hole. The star had fooled them because, by pure chance, it had been at nearly the same position in its orbit during each earlier observation, explaining why the velocity was about the same and why the star didn't seem to be orbiting anything. It's like a cop walking his beat, and every time he goes by, this person's standing next to the storefront, but he comes by every 5, whatever, 10 minutes. He's got a pattern, and if the person's always there, you never assume they moved, but they could have moved. And so when they kept catching it, it was just happenstance that the black hole, that the star was never, the velocity was always the same. So the dark object and the yellow star are about as far apart as the sun and Mars. That's not very far apart, but the luminous star races around its dark partner about 3 times faster than Mars moves. Just as Mars is much less massive than the sun, the yellow star is much less massive than the dark object it's racing around, so the star's speed primarily reflects the dark object's great mass. For a given separation, Kepler's third law says that the binary's total mass goes as the square of the orbital velocity. Because the yellow star is moving 3 times faster than Mars, the dark object must be about 3 times 3 equals 9 times as massive as the sun, actually 9.6. Such a massive, invisible object can only be a black hole. Because again, neutron star, they don't get that big. I'll get into that later here, but neutron stars, anything above like 3, they're like, no, probably more like a black hole. Because that's how they, if it gets certain size, it'll collapse down into a neutron star, but if it gets to a certain much bigger, it'll collapse down into a black hole. But despite the exotic partner being a black hole, the star itself is a G-type main sequence star like the Sun, converting hydrogen into helium at its center. The astronomers renamed the system Gaia BH1, the BH standing for black hole, with the distance of 1,560 light years. And here's interesting. That distance is very close, but here's what's really cool. They know using Gaia data, it's give or take 13 light years. So previously we went from knowing one of the most distant accurate black hole distances within 500, give or take. This is 13. Plus, it is the closest known black hole to Earth and the first discovered by the orbiting observatory. There are probably something like 1 million other black holes that are even closer, Al-Badri says. They're just hard to find. That's because the vast majority of black holes are probably single, even though massive stars are usually born with at least one stellar partner. But if a massive star explodes, the supernova can cast off so much material that gravity no longer keeps the companion star in orbit, and the surviving star sails off on its own. Essentially black, when it goes on its own, it'll implode and we won't see it. And even if the massive star merely implodes, like Cygnus X1, the collapse can kick the freshly formed black hole away from its mate, because the implosion is usually asymmetric, meaning it's not in the same symmetry, so it can send something different in a different direction. Cygnus X1 is weird because that didn't happen. Okay. The most recent development on the local black hole front came just last summer, when one now referred to as Gaia BH3 was found a little farther out than Gaia BH1. However, it came from Gaia DR4 data, which is their data release, their fourth data release. And the truth is, that thing's set to be officially released next December. Not this December, next December, December of 2026. Okay, so how did we find out about a black hole discovery from something that hasn't been released? Well, the authors said they took the unprecedented step of publishing their finding due to the unique nature of the discovery, which they write, we believe should not be kept from the scientific community until the next release. An early disclosure will also enable an early and extensive follow-up by the community. You see, the European Space Agency and their consortium, they get first crack at this data, just like we get first crack at ours from our satellites. And so they scooped this one up right away and said, whoa, this is interesting. And they went ahead and released it, which I'm proud of them for doing that. Their serendipitous discovery was a wide binary system 1,930 light years away, so not even 2,000 light years away, in which a yellow giant orbits a black hole every 11.6 years. That's why I say it's a wide binary. That's a pretty long time. But the black hole has a mass 33 times that of the Sun, which is over 50% larger than Cygnus X1 and in the mass range of the extragalactic ones detected by gravitational waves. Again, the gravitational waves are best for detecting the big ones, and we can detect some of the bigger ones even in another galaxy. But they found this one, and they didn't even need gravitational waves. So this is what they talk about multimedia messenger and stuff, where we have multiple ways to detect. In fact, Gaia BH3 now holds the record for the largest known stellar mass galactic black hole. But also intriguing is the optical secondary, which is an old, very metal poor yellow giant with a mass of only 3/4 of our Sun. It probably came from a stellar stream, since it's a high proper motion halo star in a retrograde orbit around the galaxy. As the authors of the paper note, this discovery strongly supports the scenario where high mass black holes are remnants of low metallicity stars. And what that means is that they're older stars. They haven't, the stars with the low metallicity are the ones that are like second generation. Third generation stars, like ours, known as like population 1. They have more heavier elements in them, also known as metals, and that's because they got them from other supernovas. This one doesn't have a lot of interaction, so it's probably type 2. And so they're starting to think that, high mass black holes maybe came from that. It's part of the age and the size of the star kind of thing. So still, the question remains, where is the nearest black hole? And this helps us answer it. This next part I'm going to talk about. Thanks to a recent discovery, astronomers are able to estimate that it might be the nearest isolated stellar mass black hole to Earth might be as close as 80 light years away. And they did it because when they got to see this rare event, they were able to run their models and stuff. It's kind of a guesstimate, 80 light years. We don't know, but they're trying to figure out the odds. So in July of 2011, a faint star in an extremely crowded field, less than 2 degrees from the galactic center, brightened from roughly 22nd magnitude to 16th magnitude. When I say 16th, I mean that sucker, I could have seen that in my 10-inch. That's pretty bright. It was detected by 2 independent ground-based microlensing surveys designed to monitor hundreds of millions of stars in that region. These surveys were specifically looking for objects heavy enough to warp space, since they have the ability to deflect and amplify starlight from anything that momentarily lines up exactly behind them. This discovery triggered a Hubble Space Telescope follow-up program to get involved when the schedule allowed, which is some 19 days after peak light magnification on July 20th. Over the next 6 years, observations of it were made at intervals with the Hubble Space Telescope, long enough for robust separation of the relativistic deflection from proper motion. I just love this. This is so cool. It was a painstaking process, but in July of 2022, 2 teams working independently released their results. One team, led by Kailash Sehu of Space Telescope Science Institute, found that the object, which had temporarily brightened a background star via gravitational lensing, had a solar mass of 7.1 at a distance of 5,150 light years. The other team, led by Casey Lamb of the University of California, Berkeley, found instead that the mass of the invisible compact object is between 1.6 and 4.4 times that of the Sun. So while Sehu's results indicated a black hole, Lamb's findings placed it in such a range that at the low end it would be a neutron star. Since then, Lamb has reanalyzed the data and found the unseen companion to be a black hole, weighing in at 6 solar masses. So he says 6, the other guy says 7.1. So they're basically getting on the same page now. His team's discrepancy from the early result was caused by a difference in the measured bias correction from a neighboring bright star. This new finding places this particular black hole, in the 5th spot at a distance of 5,610 light years. So this one that we found, we didn't even they just shot in the dark, basically, just happened to see it pass in front of another star and brighten it momentarily, the other star. They can tell you how far away it was, and it's the 5th closest right now. That's pretty cool. So I'm going to give you a quick rundown now of the ones I talked about and their visibility. Scorpius X1. It's been several years since I viewed it, but its current magnitude, thanks to submissions by amateurs to the AAVSO, is hovering around magnitude 12.5, placing it in the range of large binoculars or small telescopes. If anyone wants to look for it, you should know that it's currently culminating around sunset, which, means it's going to be past by the time it actually gets dark. Okay, now to Cygnus X1. To see the companion star of Cygnus X1 for yourself, simply find the 3.9 magnitude yellow-orange giant Eta Cygnus in the neck of the swan. 4th magnitude, it's not too bad. Then, using binoculars, look almost half a degree northeast for a magnitude 8.9 star with a fainter star 1 arc minute north. The first one that catches your eyes is the prize, the 8.9 star. And while looking at it, remember that this direct collapse black hole that's orbiting it formed some 5 million years ago, which was around the same time the first mammoths showed up in the fossil records on Earth. Meaning, it doesn't seem like it was that long ago all of a sudden. In telescopes 14 inches and larger under very dark skies, you should look for a bluish bow shock north of it. I've seen it distinctly with an oxygen 3 filter in a 36-inch and suspected it in the 16-inch from my backyard, the 16-inch that I own. This bow shock was created when a relativistic jet of hot gas extending out perpendicular to the black hole's accretion disk collided with dense interstellar matter. So we talk about like quasars, and then there's blazars where you're looking down the relativistic jet, and that's that's a supermassive black hole in another galaxy. Well, black holes have these accretion disks if they have a companion. This one is accreting, and then there's material that it just can't handle, and it gets sped up and shot out off its north or south, its axial poles. This one is ramming into this material around it, and it's been doing it for so long that it's created, this little different type of nebula to glow. And when you see that, oh man, that's so cool. So now we're going to go to Gaia BH1. I chased down the G-type dwarf that orbits it for the first time last summer, using just my little 5-inch telescope, so this little reflector. I found it by a careful star hop 3.3 degrees northwest of the globular cluster Messier 14. Remember, we're in Ophiuchus here, and that's Messier 14, 10, 9. Those are some of the more common ones there. With an eyepiece yielding a 3/4 of a degree true field of view at 136 power, the 14.1 magnitude star that Gaia BH1 is associated with was faintly visible with averted vision. And I will say that that star was a little faint because there was another star nearby, 1.3 arc minutes west-southwest. Oh, northeast is a 13.2 magnitude star. So you have to make sure you take your time. But the next one, Gaia BH3, it's pretty easy. It's the optical secondary of it is visible in your telescope or even large binoculars, since it lies 1.5 degrees into Aquila from the Sagitta border and is 2.6 degrees south of 4th magnitude Beta Sagittae. In fact, at magnitude 11.6, that star was bright enough to be visible last summer in my 5-inch telescope again in hazy, smoke-tainted skies. 27 power, it was visible with direct vision, 5.5 arc minutes northwest of a magnitude 9.4 star. I plan to look for it as soon as the skies get a little better for me using my Canon 15x50 image stabilized binoculars. So I'm really cool. And I will take this moment to mention that Kareem El-Badri and his team that discovered the Gaia BH1, they did discover a stellar mass black hole shortly after that. They called it Gaia BH2. It currently holds the record for third closest black hole at about 3,800 light years away, because BH3 holds the second place, so this one holds the third. Sadly for you and I, it lies in southern Centaurus at declination minus 59.2 degrees and not visible from my latitude and from a lot of people's latitude. So I'd go hunt that one if I could. When it is released next year, the Gaia DR4, the data release 4, is expected to reveal even closer black holes. So the answer still waits. Meanwhile, astronomers are pondering the chief mystery that the black holes found by Gaia pose. How did the companion star of each one manage to survive the drama that preceded the black hole's birth? That's a really big question, because you wouldn't think they could survive. That you think they'd get ripped to shreds if something that's going on. So that's the end of my talk. And like I said, I'm not much into black holes, but I have to say these kind of got me interested. The fact that which one's closest.
Well, thank you, Scott. It's always interesting there's always questions. And yeah, I mean, I have a lot of questions, and I think that's the thing you really like about black holes. There is so much we don't know, and it keeps you wondering. I mean, to think, I was amazed in the very beginning to learn that there was a black hole in the middle of our galaxy, and that just intrigued me. Just
Mm-hmm.
to even think that one would be there. And then everything we've learned since then, but there's still so much more to learn. And I think that's always going to draw people into, to a conversation. I know I gave a talk Saturday night, as I was saying, and a lot of people brought up questions about black holes because they're so intrigued about what they are, where they are. I said, tune in, tune into
Hmm.
this. So,
Yeah.
but it is, I think that's always going to be a draw.
If I can interject for a moment, Konstantin Batygin and Michael Brown, as you know, have been searching for Planet 9 for some time out of California. And this was largely based on the fact that most of the orbits of many of the Kuiper Belt objects were all reaching aphelion in the same direction from the sun,
Yeah. They were kind of.
indicating, a likely mass in the other direction. Well,
Mhm.
that's been somewhat defeated now because of the discovery now of a fairly substantial
Mhm.
Kuiper Belt object in that direction. But they were considering the possibility of a primordial black hole about the event horizon about this size, Neptune mass, that could account for the gravitational effects that have led them to believe that Planet 9 exists. And it's thought that many small black holes like this, which would clearly be dormant, like the one you mentioned, could exist in the universe. And also, I read a paper the other day by Roy Kerr, who was the one who developed the theory of rotating black holes. And his conclusion is it's hardly unimaginable. It's completely unimaginable that you could have a black hole form without some angular momentum that would cause the black hole to rotate, which would create a ring singularity. And what he concluded in a paper is that singularities may not exist as we understand them. That is, that particles entering a black hole might do something like this. I'm going to share just one slide, if I may. And here it is. And that this would be the trajectory of a particle inside the event horizon of a black hole, that it would never devolve to the center or to a singularity at all. And he wrote a paper on this, and he's a very significant scientist in black hole physics, because again, he's the one who developed all of the physics surrounding rotating black holes. But your talk is just fascinating, and I've got some new targets to add to my list.
Yeah, well, thanks for bringing up that one. When I gave this talk at the Texas Star Party, Molly Wakeling asked me afterwards, "What do I think about the idea of the mini black hole somewhere out there, Planet Nine being a mini black hole?" And I was like, I haven't even heard of that one. That's how much there is to research. I didn't know about that idea of yours where maybe matter is still traveling around inside there. And it's like, how does that? There's just so much because the closer they would be to us, the better we could study them, but the more dangerous they are. So we can't, they're like a tiger at the zoo. You really shouldn't get close enough to look them in the eye like that.
That's definitely true. All right, Scott, thank you so much.
Thank you. Thank you.
Yeah.
There was lively chatter going on, no specific questions about black holes, but
That's understandable. It's not one of those where you all of a sudden have a whole ton of questions.
right, that's right. But I think that we live in really special times. That in our era, the first image of a black hole was made. And so that's and I think about what humans have discovered and what it's taken to discover it. I just really pinch myself because it's almost completely unbelievable in the realm of science fiction, even. So, but we have things like the LIGO. We have the Event Horizon Telescope. And with more advances in science and it also advances in telescope technology, it's there's just an unending, forever stream of exploration and discoveries that will be made. So. But something I do want to encourage people to think about. We have had challenges to the scientific community, and so when you see science in your community, do everything you can to support it. There are public observatories, there are public events, there are amateur astronomers that do sidewalk astronomy. All of this stuff at the very basic level helps inspire people to take next steps. And then once they take those first couple of steps, what they want to do is join the Astronomical League, and go on that journey like Scott Harrington has, for example. So, but it was great to be on another Astronomical League Live. When is the next one, Terry?
Yeah, let me show a slide. Now, we're not going to be here in October. There were different things going on. And so what I did was I had John Goss go over and make slide for, there we go. We're going to have Alan Dyer here on November 14th, and he will be talking about traveling to great sky sites. I thought that said stars, to great sites as you travel, because a lot of us on vacation or whether we're out looking around, a lot of us kind of plan to do things around dark skies and skies that are a lot darker than most of us have at home. So we use that time. And so Alan will be talking about that in November, on November 14th. And we've got another real treat for December 5th. We are going to have Jericho Kuehl. That is a winner from the Horkheimer, I believe it was Horkheimer, was it Smith?
Service.
Service Award. He is
Sorry.
an excellent speaker. He is amazing with the work he has done. So we are really looking forward to having both of them on for AL Live. We will be back in November on November 14th with Alan Dyer. So please join us then. And then back December 5th with Jericho. So Scott, that is kind of our lineup for the rest of the year.
Is it? Okay, well, great.
Well, yep.
I also want to thank people that were watching tonight. Barbara Harris was on. Tarek Al-Hamrani from the UAE was there. Harold Locke, one of the regulars on our audience here. I know there's plenty of you that don't chat but watch, so we want to thank you too. Andrew Corkill was on earlier, and many more. So it was a nice way to spend our Friday evening and around the virtual campfire talk.
Yeah.
That is Astronomical League Live. So Scott Harrington, thank you. Chuck and Don, it was wonderful to have you on, just to see your faces and everything. So
yeah, and thank you, Scott, for all your help.
All right.
And thank you, everybody out there. And as he said, Scott Harrington, Chuck Allen, and Don Knabb, thank you very much for being on and talking to us about what's going on in the sky.
All right. Okay, so I will take us out here.
All right, Scott, thank you.
Thanks again, everyone.
Good night.
Yeah.